In this video, I'll talk about atoms with 3 or more electrons. So again, we can solve the Schrodinger equation for the 1 electron systems exactly. But if a system contains 2 or more electrons, we cannot solve those exactly. We will get approximate wave functions and estimate their energy. For a many electron system, we can use 2 different methods. One is the so-called variational method based on the variational principle. The other method is the self-consistent field method. So let's look at this lithium atom and let's try to solve the Schrodinger equation of the lithium atom using the self-consistent field method. First, we need to write out the Schrodinger equation for the lithium atom. Well, it's H psi equals E psi. H is the total energy operator. Therefore, H is the kinetic energy plus the potential energy. So where is the kinetic energy? Over here. These 3 terms are the kinetic energy of the 3 electrons. What about the kinetic energy of the lithium nucleus? Well, it's much smaller than the kinetic energy of the electrons and thus negligible. And then we have these 3 negative terms. Those are the attraction felt by the 3 electrons. For example, electron 1 feels plus 3 charge from the nucleus. Same for electron 2 and electron 3. What about electron-electron repulsion? We have electron-electron repulsion between 1 and 2, 2 and 3, 1 and 3. So over here we have the kinetic energy, we have the potential energy. The potential energy consists of attraction and repulsion. That's it. So how do we solve this equation? This equation contains 3 electrons. Each electron has 3 coordinates. It can be x, y, z Cartesian coordinates or r, theta, phi polar coordinates. But anyway, we have 9 coordinates in this equation, 9 variables. It's impossible to solve this Schrodinger equation exactly. So we will use the self-consistent field or SCF method to get approximate wave functions and approximate energy for this system. First, we need to take a guess. We have 3 electrons, so we take a guess of 3 wave functions. The first wave function is e to the power of negative 3r times alpha spin. The second one, e to the power of negative 3r times beta spin. So these 2 are the wave functions for the electrons in the 1s orbital. And then e to the power of negative r over 2 times alpha. So why this? Again, we just need to take a guess. I'm assuming the 2s electron is a bit far away from the nucleus than the 1s electrons. And I'm making approximations here. I'm putting the 1s electrons into the nucleus, and then it behaves like a hydrogen atom with a single electron occupying the 2s orbital. And therefore, I'm using this e to the power of negative r over 2 as my initial guess. Again, if you have just a simple hydrogen atom, and if you look at the 2s electron in the hydrogen atom, the wave function is e to the power of negative r over 2. And then I'm assuming the third electron has an alpha spin. And then we have to build the total wave function of the 3 electrons. And this wave function must be antisymmetric. Therefore, we have to use a determinant over here. This is the total wave function of 3 electrons, 1, 2, and 3. 1 over the square root of 3 factorial is the normalization factor. It's not very important, so don't worry about this too much. And then we have 3 rows and 3 columns. You can see I wrote phi1, 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 phi2, 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 phi3, 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 and then electron 1, electron 2, electron 3. And this determinant guarantees that if you swap electron 1 and electron 2, it's equivalent to swapping these two rows. The sign of this determinant will change. And this guarantees this wave function is antisymmetric. And then, how do we solve the Schrodinger equation for 3 electrons? The simple answer is we do not solve the Schrodinger equation for 3 electrons or even 2 electrons. We can only solve the Schrodinger equation for 1 electron. So we're going to solve the Schrodinger equation for one of the 3 electrons first, and then the second electron, and then the third electron separately. So let's look at the first electron. We're going to solve the Schrodinger equation for the first electron. But if you try to solve the Schrodinger equation for the first electron, the difficulty is this. Electron 1 is repelled by electron 2 and 3. So this repulsion contains the coordinates of electron 2 and electron 3. How do we get around this? Very simple. We define the effective potential energy operator over here. So this is the effective potential energy operator for electron 1. Supposedly, this effective operator contains the coordinates of only electron 1. First, this is potential energy. Therefore, we have attraction here. This is the attraction electron 1 feels. And this 3 is the number of charges in the nucleus. And this is attraction, thus negative. And then over here, electron 1 is repelled by electron 2. So this is the repulsion operator. Electron 1 is repelled by electron 3. This is the repulsion operator. In SI units, this one should be E squared over 2 pi epsilon R13. But again, in atomic units, the charge of the electron is -1, so -1 squared is 1. And then 4 pi epsilon is 1. 1 over 4 pi epsilon is also 1, therefore it's simplified here. Alright, but then we're going to evaluate the effective operator of this repulsion by inserting these two operators, the sum of these two operators between psi star and psi. What is psi? This is psi, the total wave function. This is psi. And then we integrate this with respect to electron 2 and electron 3. So if you integrate a function with respect to x, you remove this x in the result of the integral. So by doing this, we effectively remove the coordinates of electron 2 and electron 3. So this d tau 2 is dx2 dy2 dz2. This d tau 3 is dx3 dy3 dz3 in Cartesian coordinates. If you use polar coordinates, this d tau 2 is r2 squared sine theta 2 dr2 d theta 2 d phi 2. Alright, so we're not really going to do the math here. I'm going to just tell you in principle, by doing this integral with respect to the coordinates of electron 2 and the electron 3, we can effectively remove the coordinates of these two electrons. So this integral contains the coordinates of only electron 1. And this one contains the coordinates of electron 1. Therefore, this effective potential energy operator contains the coordinates of only electron 1. Alright, now we have a 1 electron Schrodinger equation. This is the kinetic energy of electron 1. This is the effective potential energy operator for electron 1. Together, that's the effective total energy for electron 1. We solve this 1 electron Schrodinger equation. We get epsilon 1. Supposedly, that's the energy of electron 1. We do this for electron 1, and then we do this for electron 2 and electron 3 in a similar fashion. And then we will be able to get epsilon 1, epsilon 2, epsilon 3. They correspond to the atomic orbital energy. And also we get phi1, phi2, and phi3 in red. They are the atomic orbitals. With the new phi1, phi2, and phi3 in red, by solving these three equations, we can create now a new antisymmetric wave function of the 3 electrons. Again, we'll have to use the new phi1, phi2, phi3 here to create a new psi of the 3 electrons. And then once we have this new psi, we can again evaluate the 1 electron effective potential energy operator by doing this. This time we need to use the new psi here and here. And then we'll get a new effective potential energy operator. We plug it in here, we get another new phi1, phi2, and phi3. Alright? So those phis are atomic orbitals. And then we keep doing this. We keep getting a new set of phi1, phi2, phi3. We keep getting a new psi, the total wave function of 3 electrons. And this is a antisymmetric total wave function of the 3 electrons. And we keep doing this iterations until the set of potential energy, so this V1, V2, V3 for the 3 electrons, converges. So what does that mean? So we keep doing this, we do multiple steps, but if this V1, effective V1, effective V2, and effective V3 are equal to or very close to the V1, V2, V3 of the previous step, and we say the iterations converge. We stop there, and we obtain the approximate wave functions for the 3 electrons, and also the approximate total wave function of the 3 electrons together. So that's the strategy of solving the Schrodinger equation for electron with for a system with 3 or more electrons. Now let's just talk about beryllium with 4 electrons. We have 4 kinetic energy terms, 1 for each electron. Again, we neglect the kinetic energy of the beryllium nucleus. It's too heavy, therefore it moves too slow, and then overall the kinetic energy of the nucleus is much smaller than the kinetic energy of the electrons. Alright, and then we have 4 attraction terms because each of the 4 electrons is attracted by the nucleus. How many repulsion? We have 4 times 3 divided by 2, 6 repulsion terms. This is because each electron feels repulsion from the other 3 electrons. So we have 12 electron terms. But if you say 12, you double counted every single repulsion term. Okay? And for boron, there are 5 electrons. Therefore, there are 5 kinetic energy terms and 5 attraction terms. There are a total of 5 times 4 divided by 2, 10 electron repulsion terms. For element 118, there are 118 electrons. Therefore, 118 kinetic energy terms, 1 for each electron, and 118 attraction terms, 1 for each electron. There are 118 times 117 divided by 2. That's more than 6,000 electron repulsion terms. So how do we solve the Schrodinger equation for this guy with 118 electrons? Well, it's very simple. We take a guess of 118 wave functions, 1 for each electron. Alright, and then we make a huge determinant, 118 by 118 determinant. How many terms? There are 118 factorial terms if we expand this 118 by 118 determinant. And then we can compute the effective potential energy operator for electron 1, electron 2, etc. And then for each electron, there's a simple kinetic energy term and a effective potential energy term. Put them together, you get the Hamiltonian for that electron. And then we can solve the 1 electron system. We solve that, we get a new wave function for that electron and 117 other wave functions for the other electrons. And then we rebuild the total wave function of this 118 electrons. We'll get a new 118 by 118 wave function. 118 by 118 determinant as the total wave function. It's antisymmetric. given the new total wave function, we can re-evaluate the effective potential energy operator for every single electron. And then we recalculate the wave function for each electron. We keep doing this until convergence. So that's the SCF method, self-consistent field method. If we have n electrons, so this is general, each electron is repelled by the other n-1 electrons. Therefore, we have n times n-1 electron repulsion terms. But wait, because each repulsion term is counted twice for each of the two participation electrons, and then the total number of repulsion terms is n times n-1 divided by 2. All right, so there's a similar example. Let's say each water molecule forms 400 bonds in ice. And then 1 mole of water molecules in ice can form only 2 moles of hydrogen bonds, because again, you should avoid double counting every single hydrogen bond formed by 2 participating water molecules. So same here, same philosophy here. So after you do n times n-1, you have to divide it by 2. Why not n squared divided by 2? Because an electron does not repel itself. An electron is repelled by the other n-1 electrons. All right. Let's switch to a different topic. In general, if we are looking at atoms with multiple electrons, we can analyze the behavior of those electrons in a many electron atom without doing any calculations, without solving the Schrodinger equations. But we need to obey some rules for this to happen, for this analysis to be realistic. So first, we need to ignore all the core electrons. As a chemist, we don't care about the core electrons. We care about only valence electrons. And second, you may safely ignore the completely empty or completely filled subshells. So in general, this is just to simplify the situation. If you have a carbon atom, ignore the 2s2 subshell because it's completely filled. And also, you may safely ignore the 3s, 3p, 3d orbitals because they are empty. So we just focus on the 3p orbital of the carbon atom. There are 2 electrons there. The 3p orbitals are partially filled. Rule number 3. Now let's look at the electrons that occupy the partially filled subshells. For example, the 2 electrons in the 2p orbitals of carbon. These electrons behave collectively like a superelectron. We know that for a single electron we have angular quantum numbers. For the carbon atom, there are 2 electrons occupying the 2p orbitals, and the 2p orbitals correspond to L equals 1. Okay, L equals 1 for p orbitals. L equals 0, 1, 2, 3 for SPDF orbitals. So the Z component of the angular momentum also has a corresponding quantum number, m sub L. So m sub L can be from negative L to positive L. So for p electrons, m sub L can be negative 1, 0, and 1. All right? So, but we have 2 electrons occupying the 2p orbitals in the carbon atom. Therefore, the sum of m sub L, the sum of the Z component, can be as negative as negative 2 and as positive as plus 2. So again, if both electrons has a value of m sub L being equal to 1, the sum of these 2 numbers is 2. So we'll just have to sum up the quantum numbers. In this case, the Z component of the angular quantum numbers. And also, we can sum up the Z component of the spin quantum numbers. For a single electron, the spin number can be plus half or negative half. And then if we have 2 such electrons, we sum up these 2 numbers, positive half plus positive half, we get positive 1. If we get 2 negative 1 half, we get negative 1. And then if we sum up positive half and negative half, we get 0. So it's possible for the sum of the Z component to be negative 1, 0, and 1. So again, we're talking about the collective behavior of multiple electrons now. So again, get back to this carbon atom. We focus on this 2p subshell. It's occupied by 2 electrons. And then these 2 electrons can have m sub l be equal to -1, 0, or 1, m sub s being -half or +half. This is the spin number, but more accurately, it's the z component of the electron spin. It can spin up, it can spin down. So together, we treat these 2 electrons collectively. We view these 2 electrons as a super electron with a -2 charge. This super electron may occupy actually a s orbital, p orbital, or a d orbital. Why is that? Because again, if we sum up this m sub l for these 2 electrons, you can have -1 plus -1, you get -2. And how can you get -2 as the z component of angular momentum? Well, that has to be a d orbital. So these 2 electrons may collectively behave like a d electron. And also, now look at the electron spin. If you look at an individual electron, it can be -half or +half. But together, well, if you sum up 2 negative halves, you get -1. If you sum up 2 +1/2, you get 1. And if you sum up -1/2 and +1/2, you get 0. All right, so this kind of analysis leads to a very complex quantum behavior and the definition and application of atomic terms.